welcome back. We are now starting chapter 5, and we're going to start looking at the stress from a torsion. Okay, so it's torsional, it's going to be shear stress. So what is torsion? Well, it's a moment that tends to twist. Anytime you are spinning around the centroid of an axis, you are going to be providing some sort of torque force. When we're looking at things like augers, we're going to have torsion. And when we look at the stresses that are developing, they're actually not going to be a constant torque. I mean, it's going to be a constant torque versus when you maybe have gears and belt drives where you have torque that's changing where the gears are versus like the auger where it's going to be some sort of a function with the depth that we are drilling and the type of soil, et cetera, et cetera. So this column right here is a column failure and torsion. It's usually not something that we're wanting, but if something hits it up high, it can cause it to twist. So that's what we're looking at now. So what is torsion? What does it look like? Here's a shaft. And if we were to draw radial lines along that shaft, then the radial lines that are coming from the back where it's fixed to the front remain straight. Okay. The longitudinal lines, so the radial lines you can see right here are radius. Those are remaining straight. The longitudinal lines coming from the back towards the front here are twisting. Okay, they are twisting. If we were to cut it into circles like slicing bread, we're going to see that each circle remains circular. Okay, so our slice of bread is still going to look like a slice of bread. It's going to have the same radial length and it's going to have the same diameter. And it's going to be the same thickness as we cut it. However, if we look at one end of the bread to the other, those lines are twisting, okay? If you want to look at a stress analysis, you can actually see how that stress then is affecting the cross section where we have no stress in the middle versus lots of stress on the outside as we're really trying to twist around. Here we can look at a sample rubber specimen that's had a rectangle drawn on it, a square drawn on it, and when you twist it, you can see the skewing of the shape. And so remember, with normal stress was perpendicular and it caused change in length. With shear stress, we had shear strain, which caused that skewing. So we are definitely looking at shear strain. You can look at this specimen right here and you can see as you twist, you can see the strain that develops. Okay, so that's how you know that shear stress, shear strain are associated with torsion. So let's go back and look at this shaft that's fixed at the wall and we've drawn lines on it. And here's the undeformed shape. We have not applied a torque load. And, you know, a lot of times we might think of a torque load as just I'm twisting like right here around a washcloth, but it could be anything where a load is offset from the center. Okay, so as you're trying to take a bolt off, you're going to have that moment that's created. You could have torsion about itself. So as we're starting to twist, you can see these longitudinal lines that are coming from the fixed point coming towards the front as we're coming along the length towards where that load is being applied is twisting. And we can see that angle of phi, that's going to be called our angle of twist. And we'll get to that shortly. And phi it changes along the length. Okay, so we can see that we're twisting on that cross section, but we also have that change, that twist down the length of the specimen. So let's take a closer look. If we want to look at the distance between the circles, we've already said that they remain the same. It's like slicing bread. As I'm slicing that, we're not doing shear stress slicing, but if I were to slice the bread, if I were to take it, twist it, and slice it, it's still the same distance between. We aren't changing length longer or shorter when we're looking at that bread. We're not looking at normal deformation. It's just that twisting. So the distance between the circles remains constant, so we can pull out a differential element, right? We can pull out a little differential element and then start to look at it on a much, much smaller scale. So the thing we have to remember with shear stress, with torsion, is that C equals the shaft radius. Okay, C is the radius. Why is it not an R? I don't know why, but C is literally the radius. So if we start with this little differential element, this slice, I guess you could call it, and we look inside that slice, then we can see, as we're kind of going in, we can see, okay, I have my radius, that would be C, that's the dotted line. Okay, rho is some length along the radius. So rho could be 0, or rho could equal C. It is somewhere between 0 and C. So as we are moving along rho, okay, we're going to find that the strain is also increasing. And if the strain's increasing, our stress is increasing. Because as I twist, we're twisting right around that centroid, which means there's no twisty action acting right at that centroid. But as we move away from the centroid, we're having to twist farther and twist farther and twist farther and twist farther, okay, to keep the material together. So we're going to be looking at that shear strain. Remember, that comes back from, let's go back here. That's back here from the shear strain. If we drew where this line was originally, it would be straight. And we can see that it's twisted from it. That's going to be our shear strain. We can literally see that box goes oink, okay, goes kind of cockeyed. And then phi is going to be the change on our radial, okay, our radial line. So again, rho is some length along the radius where it goes from 0 to C, and C is the actual radius, okay? And again, let's look down here. You can see, okay, you can see the twisting of that square piece. So if we could draw the line straight back on that, we would see the shear strain, which is gamma, and that's what's coming down the length of our member. Okay, so let's go back and take a closer look at this. Okay, so we know that we have a radius which goes all the way out to the out. We know that rho is some length along that radial line. And we know that we are rotating about the x-axis. We'll talk about positive, negative shortly. And this is going to create shear strain gamma. Okay, so here's the gamma. That's the longitudinal line. It's the long line. As that we start to twist, it's going to rotate. Think about wringing out a wash rag. When you're holding it like this, you can kind of see the lines of the wash rag, and then you twist, you can see that shear strain. Okay, so we rotate about the x-axis, we have this shear strain gamma. And if we think back with what we've done previously with shear strain, with a shear block, like on the last exam, we have tan gamma is d to d prime, okay, d prime to d double prime, I guess, over delta x. So that is going to be over our differential element. So that's how we can describe this angle. So gamma equals, remember, gamma equals opposite over adjacent. So d prime to d over c prime to d prime, that straight line. Okay, so that's kind of like that red line. Well, we can also describe that same distance from d prime to d double prime as if we look at the radius now and we look at the circumference. What do we know about our circumference? Okay, what do we know about our circumference? We know that this circumferential change comes from, okay, the radius times that delta phi, okay? Radius times delta phi. And in this case, because we're going from the inside out, we're going to just look at it as rho, okay? So we now have two different ways to look at d prime to d double prime. We can look at it from the longitudinal change, which is gamma, and we can look at it from the radial change, which is that twist from that we're going, the circumferences, we're moving around the circumference, okay? So now let's set this d prime, d double prime into our original equation with tangent. So we have tan gamma, that's our shear strain, equals our rho, our radial length, okay, d phi dx. So now we're looking at the twist and then along the length. And with small strains, what do we do with small strains? We just take the tangent away, okay, because it's going to be the same whether we use the tangent or we don't. Tangent and go to radians, or just take the tangent away and it's in radians. So we still have this relationship where we're looking at shear strain, and it's a function of our radial length the amount of twist we have and the amount of length we have that's twisting. Okay, now where is a maximum? Maximum is going to occur when we're at C, which is our radius. So we could also say that our maximum shear strain is when we have that full radius. So it's going to be on the outside. Those outside fibers have more strain than the inside fibers. Okay, and now that we have this, we can, let's go back to the purple. I can get back there. Okay, so this is really gamma of where we are with rho. So this is gamma rho, and this is gamma max. Okay, and gamma max, or not gamma, yeah, shear strain is the C with the radius. Just remember it's the radius. Sorry, I'm trying to I'm going the wrong way on my button here. Sorry, I'm really trying. Okay. So now we can rewrite this, and we're getting rid of this this delta phi delta x by rewriting our maximum equation and popping that in. So we now have that our strain along the radial length equals the ratio of our rho, our radial length, compared to the entire radius and the maximum. So it's a linear relationship, which makes sense. If you look at the picture, you can see that it is a linear line. So it will be a linear relationship between zero strain at the middle versus maximum strain at the outside. Okay, maximum strain on the outside. You can see it's linear. Okay, so now that we have this fancy equation, if we have a relationship between strain on the outside fiber all the way into the middle, which is going to be 0, then if we take G, which is our shear modulus of rigidity, and we know that shear stress equals G times shear strain, we can get the same equation set up for our shear stress relationship. And so what we can find here is that our shear stress also varies linearly from the center to the outside fiber. Okay, so when rho is 0, okay, that's right at the center, our radial length is 0, we don't have any stress. As we increase rho to the radius, that's where our maximum stress is, but we can see it's a linear relationship. So here's what it would look like sketched out on a cross section. So we've gone from shear strain and how we have that twist longitudinally and how we have that twist on the radius, okay? And we were able to figure out that relationship between our radius, okay, and what was going on shear strain, okay? And now we've said, okay, well, we figured out the strain, material properties gives us stress, and we can see the relationship here. So as I'm applying a torque, a torsional moment, a moment about itself, then we can see at the center, okay, where we have radius equals 0, or C equals 0, we have 0 stress, and it's going to increase linearly to the outside fiber. This is different than stress equals P over A, the normal, because we had that average. Every fiber elongated the same amount, or every fiber shortened the same amount. It was an average, so it would look like a block coming off. Here, it's a linear change from 0 and then to our maximum on the outside. Okay, so there we have it. So the shear stress, it doesn't act just on the surface. It acts all the way through. It just increases as we move radially along that radial line. Okay, so now that we have the relationship between strain and then we have the relationship between how stress is distributed, let's figure out an equation for shear stress. So if we take that cross section and we're looking at that applied torque, well, what is torque? Torque is a moment, which is force times distance. So if I look at a little differential element that's some radial length away, okay, if I look at some little element that's some radial length away, I know then that shear stress has to be a function of that force and that little tiny area that we have, okay? And I'm going to rewrite this as dF equals shear stress dA. Okay, and it's just, remember, this is somewhere along the radius. We don't quite know where it is. It's rho, it's a radial length. And I know that, well, that torque equals force times distance. Okay, torque equals force times distance. And so I can rewrite this equation. Sorry about that. I can rewrite this equation that if I have a force here and my distance away is rho, so torque equals force times rho, okay, force times rho, then I can relook at this as, well, my force up here, if I look at the force, it's shear stress dA, and then D is my rho. So I now have torque as it relates to the shear stress, my area, and rho, my distance along that radial line. And I can continue with, whoops, I can't go the right way today. I can continue along with my math, and I'm just swapping the dA over. It's the same equation. Now we're going to integrate because it is a differential element. So we're going to differentiate with respect to area, and voila, shear stress. This is our new stress equation. Okay, our maximum shear stress when we're looking at pure torsion, it equals T, which is the torque. Okay, C, that's going to be my radius. The maximum occurs at the radius divided by J, and we'll get to J in just a minute. Then we also have, well, we could find the torque anywhere along the radial length. So in that case, it's going to be T, which is the torque, times the radial length. So it could be like half the radius, okay, divided by J. And again, we'll get into J. But J is very similar to I when we're looking at bending. J is the same thing for torque. So here's our equation. Shear stress equals TC over J. For maximum, shear stress equals T rho over J for anywhere along that radial length. So let's talk about sign convention. If you take your right hand, always take your right hand, and if you will, like here's that gold cross section. I'm going to stick my hand on this side, and my thumb is going outwards, and I'm twisting towards me. So if I'm coming from this direction, this is called positive torque. Positive torque will also give me positive rotation. I'm still going to take my right hand. This time it's on the back side of that gold element. Thumb going out, thumb always going out for positive torque, and I'm rotating back. Okay, so my phi will also be positive, rotating that direction. Now, if you think about it, when I wring out a washcloth, okay, that's negative torque because my thumbs are going in. I don't know, I guess you could wring it this way too, but that's still, this is negative torque. Anyways, negative torque. You would have to wring it like, well, you don't have the proper hands to, to wring it. Anyways, this would be like negative torque. Negative torque, positive torque. Okay, so what is J? J is our polar moment of inertia. It is the stiffness of the system based on the cross-sectional area. Just like we have moment of inertia, and when we looked at beams, and a rectangle is BH cubed over 12, it's the relationship of where the area is located. The polar moment of inertia is the stiffness based on the cross-sectional area. So if it is solid, it is pi over 2 c to the fourth. And what is c? C is my radius. Pi over 2 radius to the fourth. If it's hollow, okay, pi over 2 c outer to the fourth minus c inner to the fourth. Do not do c outer minus c inner and then go to the fourth. That's not how it works, because it's really pi over 2 c outer to the fourth minus pi over 2 c inner to the fourth. Okay, so if you need to figure out a thickness, maybe the problem says, well, how thick does it need to be? And you're given the outside diameter or the outside radius, then you can use this equation to go back and figure out the thickness, because I know the thickness is outer minus inner. Okay, so pi over 2 c to the fourth, pi over 2 c to the fourth minus c to the fourth, outer minus inner. Okay, so if we're looking at pure torsion, when we were looking at our axially loaded things and we were pulling, you guys had to do a couple of problems where we cut it and you could find that internal normal, and there was only normal, no shear, but then we also had you cut it at like 60 degrees or 25 degrees or whatever, and all of a sudden we went from pure normal, pure axial to axial and shear, depending on the plane we cut. And so if we are looking at pure torsion, all we're doing is twisting, we don't have any normal force or bending or anything like that, then we are in pure shear. We are in pure shear. But what happens if I were to cut this, Okay, what happens if I were to cut this at an angle? All of a sudden, I have introduced that normal force. So as long as I cut it like my sandwich bread, okay, up and down, then I'm going to see pure shear. The second I cut it at an angle, then I'm going to introduce shear and normal. And this is always so important to understand. We cut it up and down like bread because geometrically, it's the easiest way to cut it. We are given our lengths of beams and our cross sections in this nice slicing the bread type of world. But that's not always what we need to be concerned about. The cool thing about looking at pure torsion is we're going to kind of look how this is related, but things like chalk, which I don't have a piece of chalk, but if you can get a hold of a piece of chalk and you twist it, okay, chalk is very brittle. If you twist it in pure torsion, like we're not pulling it, we're not just twist it in pure torsion, it will always fail at a 45-degree axis, at a 45-degree plane. And the reason is at 45 degrees, we've introduced the largest normal force. So when we're at 0, it's just plain shear. But as we are, looking and cutting at 45 degrees, all of a sudden we have this maximum tensile force with the shear. And so when we twist the chalk and it fails at 45 degrees, it's a tensile failure. It's not because of shear. It's a tensile failure. And so, we'll get into this with more circle, but as we cut it straight, we are at maximum shear. Okay, we're at maximum shear, and that's our red line here. Okay, as we cut this and we want to see what it looks like, I'm 0 degrees, 1 degree, 2 degree, 3 degree, 4 degree, that would be a lot of work. But we cut it at 45 degrees, and all of a sudden we have this blue, this maximum normal force that's in tension trying to pull it apart. And so you have to be very cognizant that when you look at this shear stress here at 0, it's maximum shear. Okay, as I come over here to 45 degrees, if my plane is at 45 degrees, I all of a sudden have this maximum tensile stress, and it is at 45 degrees. And now you can come over and like, wow, look at that. That's what chalk would look like if you had chalk. It's going to twist every single time at 45 degrees because it's a tension failure, not a shear failure. Okay, failure of wood due to torsion. You'll see this long crack. It's that normal force that's pulling it apart. Okay, it's kind of cool, but it's a normal stress failure. So let's see. So how do we set up these problems? We're going to see that it's the same process from here on out that we did with normal. Okay, if I have a shaft that has several gears and pulleys on it, then if I need to design this shaft or I want to find the internal torque, the internal stress, the angle of twist, I have to first draw a torque diagram. Okay, I have to first draw a torque diagram. And so I'm going to start over here at the right. I'm going to assume that these are frictionless bearings that are just holding it in place. It's allowed to spin, so the motor is spinning and it's putting power in, and power torque is being taken out because of the belts that are anyways providing power to other things. So if I were then to, what is the actual torque between C and D, I have to remember cover up everything to the left, look at your picture, and draw a free body diagram. If I want to know what's happening between C and B, again, I have to cover up everything to the left or everything to the right, draw a free body diagram, and find internal. Again, everything to the left or everything to the right. And so I have to work this just like a cake problem. It is a cake problem of torsion. It's no longer an axial cake problem. And I can actually draw a torque diagram. So now you all know how to draw a normal force diagram, shear diagram, moment diagram we learned in statics, and now you can do a torque diagram, and we can have all of these things happening at once. Okay, here's another example. If I need to find the internal torque, because if I need to find the stress or the angle of twist, I have to start with what is my internal of torque. And I'm going to do the same thing. I'm going to cut it. I'm going to stick my hand. I can see that my hand goes right back there between A and B. Coming towards me is positive. Okay, coming towards me is positive. Going away from me is negative. And so I can draw a torque diagram. And now I know if I'm calculating shear stress, this is a positive shear stress and negative shear stress and negative shear stress. If I have negative stress, I know that my angle of twist is negative. If I have positive stress, I know that my angle of twist is positive. And this is why On the cake problem, it's a little bit easier to see tension compression, but once we start adding this twist in, you have to keep up with positive beam notation so that you can get correct signage on your torque, because there's a huge difference between a positive angle of twist from positive shear stress and a negative angle of twist, okay? So what if we wanted to draw a stress block? We did that some with axial loading, where we drew the length of it, and we saw on a cross section, it didn't matter where we were, they all had the same stress block. Now that we're with shear stress with torsion, and it varies linearly with respect to the centroid, then depending on where you are, that stress block is going to have an increased value of stress as you're moving away along that axis. So it varies linearly along each radial line until you get to your radius, C, and then you have the largest there. So you need to keep that in mind. Depending on where your box is, you're going to have different values, okay? So I'm going to go and work some problems for you now. I would recommend reading through the textbook and just kind of understanding that what torque is, what the shear stress is, kind of where it came from, and really pounding into your head right now that this is a shear stress. And if you need to remember that it's shear stress, the one picture that I would say put into your brain, just smack that picture into your brain, is this picture right here. Because we could see in a tension test or a compression test, we could see that change in length until it pulled it apart. When I'm looking at shear, I can see skew. And if I can see skew, then I know that it's shear, because we have that shear strain gamma. And if we have shear strain gamma, then we're working with shear stresses. So I will start some problems shortly.